All right, chemists, let's get started. I don't know why this code keeps coming up exactly during this class. It's so annoying. I need to go complain to someone about this. So hopefully that goes away soon. We'll see. We'll see. I don't know. Maybe I can. Oh, it went away? Oh, okay, good. All right, so plan is for today is to continue on a little bit with more of electrochemistry. Just finish up the first half of these slides. I'm also going to jump ahead to the very end of this last chapter, chapter 13, to go over electrolysis. And the reason I want to do that is because most of you will do VOL here, and electrolysis is part of that lab. And so why not just do some of the calculations together in lecture? It really doesn't matter what order we do these last chapters in. It's all in the final anyway. And so we'll jump back to chapter 12, probably at the end of class, and then hopefully I can do some of these demos. And again, as an announcement, I guess I should have prepped this beforehand, but group project number 4 is due tomorrow, Friday at midnight. It is quite calculation heavy. I'm really going to be looking for those canceled units. Professional looking work that anyone off the street could understand and read and interpret. And I hope the activity is allowing you a chance to kind of look more deeply at some of our fuel sources out there and to compare them. The last part of the group project question says choose the best fuel. I don't have an answer. It's really up to you. You can use any criteria, even not from that assignment. It could be a criteria from something you find online, maybe the price per unit or something of those fuel sources. I'm really interested to see what you all have to say, and it's not really an extra credit opportunity, but an opportunity for you to demonstrate creativity so you can earn some points back that you may have lost from the assignment. So that's group project number 4. Also, I'll remind you that there is a survey that is open right now. It's in your assignments. It's due, I'm going to close it next week because I want those responses back as soon as possible. But completing the survey will give you some extra points to go towards online homework. It's not bonus or anything, but it's just a full credit assignment that's worth as much as an assignment for online homework to help boost that grade, especially if you have any late assignments. So yeah, those are my announcements. Okay, so let's continue on with electrochemistry, anode, oxidation, reduction, cathode. And so we use this equation to calculate the cell potential at standard conditions for any cell that we put together. All we need to do is identify what is the cathode, what is the anode, and we subtract the two values as long as they're both in the reduction form, where reduction is the gain of electrons. So all 3 of these reactions are written in the reduction form. I know they're reduction because there are electrons in the reactant side. So your reactants are gaining electrons, so they are therefore being reduced. And so in this question, I asked you determine the reaction that produces the largest cell potential. So you're looking for the largest cathode-anode combination to give you the largest value here. And so we said that, okay, this third reaction should be the cathode because it's the most positive, it's reduced the most, it's the easiest, versus reaction 1, it's not very spontaneous in the forward direction as written, but it's very spontaneous in the reverse direction in oxidation. So we said that this -1 would be our anode. And so if you put a negative value and subtract it, it ends up being positive, you get a nice big positive number out there. And so I had you predict the standard cell potential of that cell. What is the answer? It would be 1.35. That's the largest possible positive number that you can get. It's from reactions 1 and 3, where 1 is the anode, 3 is the cathode. And so the follow-up question here is, okay, write the balanced redox reaction that's actually happening. We already identified the anode as reaction 1 and that the cathode is reaction 2, but we want to make sure that those electrons cancel and that the anode is represented as an oxidation reaction. So for reaction 1, we actually need to flip it first. So that's what I have here. I've flipped that original reduction reaction to make it oxidation. Note how now the 3 electrons are on the opposite side. So you can clearly see the electrons are funneling from the product side in your anode to your reactant side in your cathode. And then you want to make sure that the number of electrons cancel and match. So we multiply by this multiplier here. To ensure that both sides you are canceling out 6 electrons, but we want to make sure that that coefficient goes across the whole way. So I'll go ahead and spread out that coefficient for everything, so I'm confident in my adding. So 3 of these, 3 of those, I already did 2 electrons times 3 is 6 electrons. There are 3 I minuses and 6 hydroxides, and now we can add up those new coefficients. We see that the electrons, those 6 electrons cancel. N is actually equal to 6 here if we needed it, and then go ahead and add that up. 2 golds combine with 8 bromides, combine with IO minus, oh no, 3 of them, sorry, forgot the coefficient, plus 3 waters. All of those things combine to give 2 gold bromide compounds. The 6 electrons cancel, and then 3 I minuses and 2 hydroxides. Or sorry, yeah, 6 hydroxides. Those 2 numbers are wrong. I keep forgetting the coefficient. 3 I minuses and 6 hydroxides there. All right, so that would be our full balanced reaction. Make sure you flip the reduction that's occurring at the anode because it should be oxidation, and then multiply by coefficient to ensure that the number of electrons cancel. All right, so how else can we use this equation? In this example, I give you a series of cells and some known values, and you should be able to figure out, okay, what's the missing cell potential of some unknown compound? And really what we're doing is utilizing this equation, E cell, standard cell potential, is equal to reduction at your cathode minus reduction at your anode. So we just have to be really careful of identifying in each of the cells, what is my cathode, what is my anode, calculate the missing piece. Because in both of these cells, I give you E cell. See, I give them to you. So one of these things is being reduced, it's the cathode. One of these things is being oxidized, it's the anode. And so we can determine the missing piece with these pieces of information. Sorry, this should not be an X, this should be a copper. So I'm trying to give you the reduction potential of copper. That's a mistake. So this should be copper solid. I'm trying to give you what the standard reduction potential of copper is, and that's going to help us determine what's going on in cell 1. Because if we look at cell 1, I know the reduction potential of copper, but in this reaction, is copper being reduced? It looks like it is. It's going from a oxidation number of +2 to 0, so it's being reduced. It is the cathode. Therefore, nickel solid is the anode. It's being oxidized. Its oxidation number is going up. Its charge is going up. So it is the anode. So I tell you the reduction potential of copper. So if we use this equation here, our E cell cat minus anode, I'm just going to copy it over here because we'll use it again. I know the cell potential of cell 1. I know the reduction potential of my cathode, it's copper. I now want to calculate what is the reduction potential of my anode of nickel. That's the missing piece. So we just plug in everything that we know. The measured cell potential is 0.62 volts, equals the reduction potential of copper, which we identified as the cathode. I give it to you right here. It's 0.34 minus the reduction potential of your anode. So in this case, it's nickel. So whatever that missing piece is. Can I do math? No, I can't. No, I can't. 0.34 minus 0.62. So I get that the reduction potential of nickel, the nickel species here, is negative 0.28 volts. So if we looked it up on a table for nickel, we should find something like 0.28 volts, hopefully. All right, but that's not what we want. I am asking you, what is the reduction potential of X, this missing piece that comes up in cell number 2? So we're going to use this nickel information for the next part, where, again, we have to identify X is being what here? It is being reduced. So it is the cathode, while nickel is the anode again. It is being oxidized. So in this case, anode, I know the information about nickel. I actually don't know the information about X, but I do know the overall cell potential. So for cell 2, this is the equation I'm using for cell 2. I know the cell potential. I know the reduction potential at the anode this time. I don't know the cell potential at the cathode. So here is X, this one is nickel. So you just plug in those numbers. Again, as long as you work with everything in reduction potentials, you're fine. You never have to flip anything. Just always work in reduction potentials. So the measured cell potential for this second cell is 0.52. Reduction potential of your cathode, this is what we're trying to calculate. So that's my unknown. And then the reduction potential at the anode for nickel, we calculated before, is negative 0.28 volts. All right? And so what you should get, yes, is that this missing piece, the reduction potential must be 0.24 in order for all of those numbers to work out. For the reduction potential of X, our unknown substance here, all right? So in this example, it's identifying what is the anode, what is the cathode, putting in the appropriate reduction values here. It looks like we have 3 different reduction values we worked with. And so if I wanted to put all of them together to kind of summarize them, it would be like this. I gave you the reduction potential of copper. That was something like 0.34 volts. That was the reduction potential. We calculated that the reduction potential of nickel, I keep writing zinc, nickel, its reduction potential, each of these are +2 electrons. We calculated was negative 0.28, and then we have this mystery X compound, 2 electrons. Its reduction potential would be something like not negative, it's positive, we got it to be positive, would be positive 0.24 volts. And so these are the values you would find on the reduction, standard reduction table like in your textbook. And so we see that of all of these compounds, copper 2+ is the most easily reduced because it has the most positive value, but X would come next, but nickel is the hardest to reduce here. And that's kind of why it showed up as the anode in all of these examples, because it has a fairly negative reduction potential. So that just kind of summarizes all that information we used on this slide. All right, so a couple more slides here, and then we'll go on to electrolysis. And this is a concept of kind of the difficulty of this chapter is we're talking about oxidation, reduction, and recognizing that they're opposites of one another, but we have to be very careful about the language we use and what we're trying to communicate of what's happening in a chemical reaction. So I mentioned, I can say, all right, a substance can be oxidized or it can be reduced, or a substance can act as an oxidizing agent or a reducing agent. So I don't know if you remember how we assigned those. Something that is oxidized in a reaction is actually a reducing agent. Something that is reduced in a reaction is the oxidizing agent. So it's all about language here. So let's go through these examples. Okay, I have a redox reaction here. A plus and B gives me A solid and B plus. So I try to make it real easy. All right, so if you do your oxidation numbers, again, it's basically charged, +1, 0, 0, +1. What substance is being reduced? Really, this should be singular. What is being reduced? What substance? Tell me, just yell it out. A, is it A is being reduced? It's A plus is being reduced. It's not A, it's A plus. You gotta be real specific. So in this case, A plus, I'm pointing to a reactant. I'm not pointing to this. This is a product. That's what you get eventually. In this reaction, A plus is getting reduced to A solid. So that makes A plus a what if it's being reduced? A oxidizing agent. So A plus is an oxidizing agent, the cation. Okay, then what substance is being oxidized? So again, singular. What do we think? B. Is it B solid or B plus? Which one is being oxidized? It's just the B solid, yes. Again, we are pointing to the reactants. B solid is changing its oxidation number from 0 to +1. So therefore, what is the reducing agent? B solid, yes. Notice how they are the same answer, but they're worded differently. So if I ask you what is a reducing agent in the back of your mind, you should change that question to what is being, what did I say? What is the reducing agent? Then what is being oxidized, right? So you don't have to memorize two things. They're both just the same question, it's just asked a little bit differently. All right, so here are the reduction half reactions for these two reactions. So here A, there's the reduction potential, there's B, there's its reduction potential. Okay, based upon these numbers, what substance is the most easily reduced based upon these numbers? We can think which one has the most positive reduction potential. That's the one that's going to be the most favorable, the most spontaneous in the forward direction. So we obviously see that that first one, A, has the higher, more positive reduction potential. So A plus is going to be more easily reduced. So if A plus is the most easily reduced, which is the stronger oxidizing agent? A plus or B plus? It's going to be A plus again. Yeah, the thing that is most easily reduced is going to be the strongest oxidizing agent. So again, these are the same question. For both of these, you are looking for the most positive reduction potential, all right, and then pointing to the reactant. Here, B plus, yes, B plus is reduced, but it doesn't produce as much of a voltage. So yes, it's spontaneous, but not as much. It can still be an oxidizing agent when it's reduced, but just not as much as A plus. Okay, so reduction reactions and oxidizing agents, those ones students usually can get fairly easily because you're just reading reduction tables as is, as given. Because when you go to a textbook, you're always going to find reduction tables. Will you ever go to the textbook and find oxidation half reactions? You won't. Because an oxidation half reaction is actually just a reduction reaction, half reaction, but reversed. And so book publishers, they're going to save space and assume that you understand that and can just read the graph backwards or the chart backwards. So here, I went ahead and reversed these two, those two half reactions. See how I have A plus being reduced to A0, B plus being reduced to B0. Note in these oxidation half reactions, I've just reversed it. I'm now going from A solid to A plus. The oxidation number is going up. B solid to B plus, going up. So if we reverse the reaction, what do you think we do to the potential of this half reaction? We probably just flip the sign, that's it. So, but here's the thing, the new potential is no longer a reduction potential. It's actually an oxidation potential now. So the oxidation potential of A solid is now negative 1.0. The oxidation potential of B solid is negative 0.2 volts. All right. So based upon these numbers, use the same method as before. We're always looking for the most positive numbers for spontaneity. Which substance is the most easily oxidized, A or B? Which one is the most positive? You might be thinking, well, they're both negative, but one of them is more positive than the other. So which one is more easily oxidized? It's B. Yes, B is the more easily oxidized here, B solid. All right. So then which substance is the strongest reducing agent, you think? It's going to be B, yes. So really, strongest reducing agent really means most easily oxidized, much like strongest oxidizing agent meant most easily reduced. It's the same exact question, and I want you to recognize that for both of these things, for whether you're looking for ease of oxidation or ease of reduction, you're looking for the most positive version of that specific equation, and in this case, it's the oxidation potential. So what I want you to see here, all right, so let me go back to the reduction potentials, because that's what you're always going to look at, is the substance with the highest, most positive reduction potential always is really easily reduced. But if you think about the reverse reaction, if A plus is very easily reduced, A solid is going to be really difficult to oxidize. There's this like trade-off. You can't be good at two things. You can only be good at one thing. And the better or like the easier it is to reduce something, the harder it is to reverse that reaction. So for B, it's not as easy, all right, it's not as easy to reduce B plus because its reduction potential is a less positive number. So therefore, B is going to be really easy, or just, I guess, easier to oxidize it. All right, so it's kind of like this trade-off. You can't be good at two things. The better you are at one thing, the crappier you are at the other thing, right? And we'll talk about this with acids too. Okay, no, never mind. We don't do that in this class. Never mind. But yeah, it's this trade-off because reduction and oxidation reactions are reverses of one another. And this is really important because the next slide gets kind of tricky in terms of wording. It's a lot of reading comprehension. Okay, so now let's actually put it together. This is the stuff you're good at, is predict the overall cell potential. Yes, we just go ahead and calculate E cell. We recognize is the reduction potential at your cathode minus the reduction potential at your anode. We can go ahead and just ignore these oxidation potentials. That's just good for predicting ease of oxidation. Really what we want to just stick with are reduction potentials because that's what we're given from the textbook. So we just have to identify what is being oxidized at my anode and what's being reduced at my cathode. So this A plus A reaction is where? At my cathode or at my anode? Just yell it out. Cathode, is it? Plus to minus, yes, it's going down, so it's cathode, perfect. And then B to B plus is then therefore at my anode. So we go ahead and subtract these two things. So cathode minus anode, so 1 minus 0.2, so we get 0.8 volts is what we should measure here. As how it's written. Because A is the cathode and B is the anode. All right, so hopefully this helps. Let's see if we can't put this all together with actual substances. Tell me, on this chart, which substance is the strongest oxidizing agent? Oxidizing agents get what in a reaction? They get reduced, okay? So the strongest oxidizing agent is going to have a large value of its reduction potential. So what substance is the strongest oxidizing agent? Silver what? Plus, very good. It's not just silver solid, it's silver plus. It's the reactant that's in the reduction potential half reaction. And then therefore the weakest oxidizing agent is going to be the most negative. Yeah, the first one we look for the most positive reduction potential. Now we're looking for the most negative reduction potential. This one is going to be zinc 2 plus. Again, we're looking at the half reactions in the reduction form. So here, this direction is reduction. Because now in the follow-up, I'm asking what species is the strongest reducing agent. Reducing agents are oxidized in a chemical half reaction. These reactions, as written in the forward direction, are they Oxidation reactions. They're not. They're reducing reactions. So you need to actually read these reactions backwards, right? So when we read them backwards, this is an oxidation reaction where now your reactants are these products. So the strongest reducing agent is going to have the most positive oxidation value. So therefore, it's the most negative reduction value. But you want to point to the right substance. So we said that silver plus was the strongest oxidizing agent. What we're going to see here, the strongest reducing agent is actually zinc plus, because it's the most negative reduction potential that's in the product side. So here we see the strongest reducing agent is zinc solid. And so the follow-up here is, what is this weakest reducing agent? So this is going to have the most negative oxidation potential, the weakest oxidizer, the thing most weakly being oxidized. So therefore, you're looking for the reaction with the most positive reduction potential. So that would be silver in this case, silver solid. So again, it's this opposites thing. Look and see what is the strongest oxidizing agent. Its product is the weakest reducing agent. Or if you look at the species with the weakest oxidizing agent, zinc plus actually has the strongest reducing agent. So the better at one thing you are, the worse you are at the other thing. All right, can't be good at two things. Okay, so again, reading comprehension. H plus can oxidize which of these species? So if H plus is oxidizing these things, it is being the oxidizing agent. So that means in the reaction, H plus is being reduced. It is the cathode because it is the oxidizing agent, H plus. So that means to answer this question, we really need to just know, okay, we want to know when is E cell positive. That's what we're trying to calculate here. We just determined that H plus is your cathode because it's being reduced. It's doing the oxidizing here. And so if you look at this table, H plus has a standard reduction potential of 0. And so we can place that 0 in the correct spot for our cell potential calculation. H plus is my cathode, so the 0 goes right there. So we need to ask ourselves, what is my anode? What can my anode be so this number comes out to be positive? If I put a negative number in here, then I can get a positive number come out. So let's look at my two options. Either I can put copper 2 plus, copper solid, lead 2 plus, or lead solid. Those are my options, all right, to choose. But let's think about this. So I already identified my cathode. Whatever I'm putting in as my anode, what kind of reaction is happening? Oxidation or reduction? Oxidation. So remember, all of these reactions, they're written in the reduction form. So lead 2 plus and copper 2 plus, these are never going to be options because those are the reactants in the reduction form. So I'm asking, should I put lead or copper in to this system because those things have the potential of being oxidized? So put those two numbers in. Only one of them will produce a positive cell potential. Which one is it? It is lead. Okay, if you put 0 minus negative 0.126, you get a positive number come out. Versus, so that was for lead, but for copper, you put a positive 0.337 and you get a negative number come out. So it's non-spontaneous. So what does that mean? H plus is acid. Acid can oxidize lead. It can dissolve lead. But acid cannot oxidize or dissolve copper. So what would you rather have your house made out of? Your pipes, your running water. Copper pipes or lead pipes? Copper pipes, yeah. right? And look, here's a reason why. Because lead slowly dissolves away, has a positive cell potential value. It's spontaneous for acid to dissolve away lead, and that's why leaded pipes are such a concern. Obviously, when someone decided, hey, let's just make lead pipes everywhere, they obviously did not look at reduction potential tables, all right, and see that, oh, lead will dissolve away in just a little bit of acid, though copper will not, all right? So that's, again, a big concern for lead pipes that are out there. Okay, let's do one more here, and then we'll skip to the end and talk about electrolysis. And I'll tell you a funny story where I was really dumb when I was a kid. Actually, I wasn't a kid, I was just a young adult. Okay, and so again, reading comprehension. Zinc can reduce which of these species? So zinc is acting as a reducing agent. So therefore, zinc is being oxidized in the reaction. So therefore, zinc is what component of the cell? The anode, yes. So that means when we put together this cell potential expression, we already know the reduction potential at the anode. We're going to just put in the appropriate things at the cathode. So the anode is going to be the zinc half reaction. So I have that here. Where is that? So zinc is negative 0.763. So basically I'm asking, what values can we put in for that cathode for a positive number to come out, right? And so we are reducing species. We want to reduce these things, so let's just be kind of clever about this. Reducing means lowering your oxidation number. Is it possible to lower lead's oxidation even more and like get something that we've seen before? Does lead minus, do we ever interact with that? We don't. So lead is not going to be an option here because we're talking about reactions at the cathode, which is reduction. Notice here all of these reduction half reactions start with cations, and we make neutral charge like metals. So we're not going to be choosing any of the metals here. Much like for the previous example, we didn't choose any of the ions. So it's going to be one of these ions that we can actually reduce to their actual metals. So if you plug in these two numbers, all right, so we are subtracting a negative 0.763. What kind of numbers can we put in there? So if we put in silver or if we put in lead, I believe lead, a positive number does come out, yes, if you plug in this 0.126 number, or you also get a positive number if you plug in that silver plus reduction potential as well, right? But it was up to us reading and understanding what's happening in this reaction to recognize that zinc is being oxidized because it's a reducing agent, so we knew to put that reduction potential in the anode compartment while we just picked and chose which number to put in the reduction or the cathode compartment. So our options were lead, 2+, or silver. Both of those end up with positive cell potentials at the end, right? And so this is kind of one of the harder parts of the chapter, definitely, about reading it and understanding what's happening in the reaction when you're not explicitly given a chemical reaction. I definitely see there's a lot of confusion with this, but we'll practice it. Okay, so we're gonna go to the very end of this chapter just to cover electrolysis. So it'll help with the VOL lab, and then we'll go back to chapter 12, and then hopefully I can do some demos at the end. So we're gonna skip cell potentials and equilibrium, but we will come back to it. Actually, it seems like we're gonna do all of the equilibrium stuff all at once. So we'll talk about batteries later, so we'll end there. I actually want to talk about electrolysis, which is a component of electrochemistry, but it's a little bit different. In previous parts of this chapter, we were always looking for positive cell potentials. That's what we wanted. Positive cell potentials mean spontaneous, that if I put together a cell and it makes a positive voltage, if I put my alligator clips on it, I can turn that little pinwheel, right? And harness that voltage and that work that can come out. Well, We've talked about spontaneous reactions, but we live in a day and age we can just plug anything into an outlet to force non-spontaneous reactions forward. So here's an example and a little slice of history, but I'm not very good at talking, like doing history. I don't even know what came first, World War I or II, but a little slice of history. So here's an example of a very non-spontaneous reaction. So the reduction of aluminum 3+ to aluminum solid is very not favorable. It's very non-spontaneous. Why? Very negative reduction potential. So in this direction, the reaction doesn't, aluminum 3+ does not want to convert to aluminum solid. But think about the reverse reaction. It is spontaneous, so the reverse reaction, the oxidation reaction, is rather spontaneous. So what this means is on Earth, aluminum solid is actually really, really hard to find. You can't just dig in the dirt and find a hunk of aluminum, believe it or not. You always find aluminum in the form of aluminum oxide, right? So yeah, you can't go around and find a hunk of aluminum. On the other hand, you can find hunks of like iron or copper out in the world. I mean, they had ages like named after that. They had like the Copper Age, the Iron Age, or the Bronze Age, right? The Iron Age, all those different ages based upon metals that they were able to smith during these times, because they were plentiful, they were available, they could smelt them using processes and mechanics that already existed at the time. Aluminum is special because the only way we can make aluminum is by electrolysis, forcing it to electrochemically. And this was not actually invented until recently. Okay, so here's a graph of the price of aluminum per metric ton over the past century. And so you see that the price of aluminum was crazy prior to the 1920s. But it was after then, now it's very much equalized, okay? So back in like prior to like the 1900s, prior to this 1920 date, aluminum solid, elemental aluminum, again, very, very hard to get. So much that the United States, when we built the Washington Monument, it was created in 1884, I guess. I guess the United States, we wanted to show off our wealth so much to the world that we topped the top of the Washington Monument with the most expensive material known to man at the time. And you know what that was? Aluminum. So the top of the Washington Monument is topped with 6 pounds of aluminum because it was expensive at the time. Okay, what do we call like fancy dinnerware? There's you know, we have china, and then next to it we always have silverware. We call it silverware because silver is a precious metal. But back then, rich people who wanted to show off their wealth actually ate off of aluminum. Utensils, which is funny to us. We're all laughing because now we just wrap our leftovers in aluminum foil, right? And so the idea here, and what I'm getting at, is that electrolysis, the invention of it, this discovery of it, unlocked a whole new age. We are in the aluminum age, I guess. Probably not. Probably more like plastics. But what was unlocked was the aluminum age, that we made aluminum so widely accessible to everybody that the price just plummeted, all right? And we were able to do it through electrolysis. Essentially plugging it into a wall and forcing this reaction to go forward. That's what we did. We plugged it into a wall. So how do we calculate this electrolytic process? Again, this is something that you do in the VOL lab. You do this exact calculation. So I wanted to do it with you. So in order to plug something into the wall, you have to provide it current for a set amount of time, and that tells you how many electrons you can deliver to your sample. So as a reminder, an ampere, an amp, what'll get you by in this part of the chapter is just knowing that an amp is equal to a coulomb per second. That's what you need to know. So if I have a sample, or if I have a current and I'm running at 5 amps, that means I'm running 5 coulombs of charge per 1 second. That's what that means. Coulomb is a unit of charge. We can measure that, charge differences. What we can't measure are like individual electrons. So this is where we use Faraday's constant, and I'll introduce this in a little bit. We use Faraday's constant to help us convert between the charge that's delivered by 1 mole of electrons. So this is Faraday's constant, but as a conversion factor, it's much more useful to us. So here I'm telling you that 1 mole of electrons is equal to 96,485 coulombs of charge. And so this conversion factor of Faraday's constant and what an amp is will allow us to convert a time unit to how many electrons were delivered in a process, all right? Okay, so let's put it all together. Really what this is just advanced dimensional analysis. It's not even advanced, it's just dimensional analysis and unit canceling. It's fancy unit canceling. All right, so here's a question. I deliver 150 amps or 125 amps for 120 seconds. How many moles of electrons are delivered? So my strategy here, just note an amp is a coulomb per second. So rewrite that as 125 coulombs is delivered every 1 second. That's what that means. Great, because I know how much time I started with. If I start with 120 seconds, I can use that amperage for every 1 second, 125 coulombs has elapsed. Now I know how much charge I delivered in that time. But I don't want that. I want how many electrons were delivered, right? So this is where Faraday's constant comes into play. So here's Faraday's constant. 1 mole is 96,485 coulombs. So in my next fraction, where am I going to put that 96,000 number, on the top or the bottom? On the bottom, yes, because you want those coulombs to cancel. So 96,485 coulombs is 1 mole of electrons, and then you're off to the races. You see, okay, seconds cancel, coulombs cancel. This is exactly how many moles you delivered in that time span, and all you needed was how much time elapsed and your current. That's all you need. And then with Faraday's constant, you know that 0.031 moles of electrons were delivered in that time. All right? Those electrons can go on to do great things, reduce a bunch of things for us, such as aluminum. But here's the thing. I delivered this many moles of electrons, but for 1 mole of aluminum, how many electrons do I need? 3. So really, this is just stoichiometry. For every 3 moles of electrons, I can only react 1 mole of aluminum. So 1 mole aluminum, 3 equals 3 moles of electrons. So really it's just using the half reaction, using the stoichiometry of the charges that are there. So let's see, how many moles of electrons does the Washington Monument need? So the Washington Monument has 2,700 grams of aluminum. Okay, that has a molar mass of 27, so 27 grams is 1 mole of aluminum. And so we can go ahead and convert for every 1 mole of aluminum, I need 3 moles of electrons. So in order to convert all of that aluminum 3+ into aluminum solid, I actually need to deliver 300 moles of electrons. So I could go ahead and use Faraday's constant and a current to get a time of how long we need to do that. Using the same strategies as above. So let's just do 2 more examples of utilizing all of these units. Okay, so let's do this exact thing. Okay, we're going to use electrolysis to turn aluminum 3+ into aluminum solid. That's what we want to do. So we're going to direct a molten sample of aluminum oxide for 3 hours, so 150 amps for 3 hours, with the goal to convert this to aluminum solid. This is how they make aluminum. Okay, it takes a lot of electricity to do it, but it's a lot easier than other methods that they used before. So let's predict how much pure aluminum in grams can be made, assuming 100% efficiency. So here's our strategy. You first take the time. You convert this to coulombs by using your amps, because amps means a coulomb per second. Next, once you're in coulombs, you're going to use Faraday's constant, because Faraday's constant tells us the relationship between coulombs, so 96485 coulombs is 1 mole of electrons. Then to get moles of metals, you're going to use the half reaction. So in this case, and stoichiometry, for every 3 moles of electrons, that only gets you 1 mole of your metal, half reaction. Basically, this is your N value from your half reaction. And then it's just molar mass at the very end to get to the gram of metal, right? So let's just do exactly that. We do this for 3 hours, but we need to get it to seconds, because if we look at this amperage, 150 amps is 150 coulombs per 1 second. That's what that means. So let's get this hour to second. 1 hour is a lot of seconds, 3600 seconds, I think. Okay, or 60 times 60. So now that I'm in seconds, I can use that amperage. So for every 1 second, I deliver 150 amps. That's really the key to unlocking how this unit canceling works, that an amp is a coulomb per second. So I think in the pre-lab, they give you milliamps a lot, so you have to convert that back to amps probably to work with it. Okay, so there's your coulomb. Oh, sorry, 150, not amps, coulombs. And then you use Faraday's constant, so you deliver 96,485 coulombs for every 1 mole of electrons delivered. Next, I don't want how many electrons I make, I want how much aluminum I make. So in order to reduce 1 mole of aluminum metal, I need 3 moles of electrons. That came from the stoichiometry of the reaction. 1 aluminum, 3 electrons. You can also tell from the oxidation numbers. And then finally, now I'm in moles of aluminum, so I just use the molar mass. 1 mole of aluminum is 27 grams. And we get that this process running for 3 hours at 150 amps only creates about 150 grams of aluminum. And so this is kind of why. Look at how much energy was required and for how long. Just to make a little bit of aluminum, it's really energy intensive to refine aluminum from ore, which is why when you think about recycling, what's like the #1 thing people recycle? It's aluminum cans, because the cans, once it's turned into aluminum, it's easier to recycle that and just shred the aluminum and remold it back to something else that's aluminum than to just use electrolysis to turn it into something else. It costs a lot of energy to do that. And so aluminum is one of those things that you should be recycling because of how energy intensive it takes to turn that ore into the refined metal. Right? Okay, so one last slide and then we'll go back to chapter 12. Okay, so here's my dumb story. I don't know, did I ever talk about like the crunchy Pinterest moms who slather coconut oil all over their bodies, or they use vinegar and baking soda to clean everything in their house? You know what I'm talking about? Yeah, so I used to be a crunchy kid when I was in college. Well, no, I wasn't crunchy. I was just kind of crunchy. It was my ex-boyfriend. He was crunchy. He was really into like homeopathic stuff. Yeah. And so I got sick one day. And he told me, he's like, here, let me make you some homemade colloidal silver. Does anyone know what that is, colloidal silver? This one dude drank a cup of it every day in his life, and his skin turned blue. Google it. Yeah, have you heard of the guy? He drank, basically it's a silver solution. It's not like silver nitrate or anything. It's a nanoparticle suspension of silver particles, and he just drank it every day. But here's the thing. This is the thinking behind it, that silver has antimicrobial properties, and so it's like, oh, drinking it, it'll make you, I don't know, less bacteria. It's like the idea of people who put gold, like the alcohol company that puts gold in their liquor. Does the gold do anything? No, but it looks cool, right? So colloidal silver really is just that. It's a homeopathic, not really to does anything, but anyway. Here's the thing. It's a common cure used in the homeopathic community. You can buy it at Walgreens for a crazy amount of money. For 4 ounces, so a tiny, tiny bit. It costs $21, but I actually took this picture 3 years ago, so I don't know how much it is now. It's probably a lot more. So it's really expensive for a little bit. And so maybe this is why me and my crunchy ex got along. He was also really cheap. So he made it himself via electrolysis. So instead of buying it at Walgreens, he made it himself. And so he made it, and I drank it. And so what I want us to do, I want to show you his setup. This was the setup, okay? Because it gets real janky, all right? It's electrolysis. What it was is he took 2 silver dollars. 1 silver dollar was the cathode. The other silver dollar was the anode, okay? Because in order to, and so what he did is he literally took those 2 silver coins, submerged them in distilled water with a little bit of salt, and then he plugged it into the wall. And then he let it go for like overnight. And remember, one is the cathode, one is the anode. There's reduction happening, there is oxidation happening at the other side. And so what would happen is at the reduction reaction at the cathode, what happens when you reduce, you go from cation to metal. So at the cathode, the silver dollar would get fatter. All of the silver would deposit on the cathode. And then on the anode, it would whittle away. And so over time, if you looked at his 2 quarters, one of them was nice, big, fat, and chunky. It was the cathode, and then the skinny one was the anode, all right? And so that depositing of one silver dollar to the other, this process was not 100% efficient, so some of those particles would stay in the solution, and that's what made the colloidal silver thing that, you know, you buy for $20, $30 for a couple ounces at the store. And so he did this overnight, and I drank it the next day. I don't know why. I got really sick. I broke out in hives because turns out I'm allergic to silver. It was really bad. So I really don't suggest doing this. So here's the thing. That was his setup. Honestly, it was ingenious. And I love telling this story every year because it shows my humility that I can be stupid too. But you can buy this device for money on the internet. All right, so look at this. You can buy this for $300 where it's 2 silver electrodes on a cap you can put in a mason jar and plug into the wall. And it does the same thing. It makes your own colloidal silver. But it does nothing. Or you could be like me, okay, and you could learn that you're allergic to silver, okay, and you don't want that stuff ingested inside of you. It was not nice. I did not get better. I'm normal now. I just take Tylenol like normal people when I get sick. Okay, so that's my humbling story. So let's talk about how long will it take to deposit 5 grams of silver on the other coin. All right, 5 grams will jump off of one coin, off of the anode, onto the cathode. So let's determine how long that'll take if we run the current at this with this amount of efficiency. So really, we are doing the exact same process, but in reverse. So in this question, we started with time and went to grams. We're just going to go to grams to time and figure out how long it takes to deposit 10 grams of silver. So note here, how many electrons are involved in this process? What is N? Show with your fingers. Just N. How many electrons to reduce silver? Look at the half reaction. Yes, just 1. So here we're going from silver plus to silver 0. So it's just 1. The stoichiometry here is just 1 to 1. So do be aware of that depending on what metal you're reducing, it changes there. So 5 grams of silver. We're working backwards. So metal, grams of metal, moles of metal. So molar mass is 107.9 grams, 1 mole of silver. Here is now where you use N, the number of electrons based upon the electrolysis, but here we're just going between silver and silver 1. So this is 1 mole of silver is 1 mole of electrons. Now that we're in the electron world, we can use Faraday's constant and amperage and stuff. So 1 mole of electrons is 96485 coulombs. And now with those coulombs, we can use that amperage that's given. So the amps is 1.150 coulombs per 1 second. And that allows us to get into a time. So 0.150 coulombs is 1 second. This is probably going to be a really big number, so I'm going to go ahead and convert this to hours. So 360 seconds is 1 hour. And when you do that, you get about 8.5 hours, almost, okay? 8.26 hours, so yeah, that's about one night's worth of sleep, of running that electrolysis setup and then drinking some in the morning. 5 grams of that silver should deposit on 1 silver dollar to the other. He would always reuse the silver dollar. He would just like swap them. He would just like swap the anode and cathode so that they would just jump back on the other one. Yeah. Honestly, I was just impressed that he was able to come up with that himself. He wasn't a chemist or anything, okay? And he was cheap like me. He refused to purchase it from a reputable seller, but instead made it himself. Okay. All right, so we'll stop there. So based upon what we've gone through today, we did about half of chapter 13. So the first part of this chapter 13 homework is due. We will finish this half of the rest of chapter 13 next week, but we are going to go jump back to chapter 12 and talk about acids and bases, but we're probably not going to finish that part of the chapter today. So I believe that we're only going to have 1 homework assignment due, and it's chapter 13. Yes, we're going out of order, but again, it doesn't matter. All right, doesn't matter. So this first chapter homework will be due. Yeah, okay. All right, so let's go back to chapter 12. All right, because I want to do my demo. I got, 20 minutes? Let's do the demo. Okay, so we talked about acids and bases. That's what we're talking about right now in this chapter. We talked about acidity, pH scales. All right, pH equals negative log H plus concentration. P just means negative log of something. It's just a function. pH means negative log of H plus concentration. POH means negative log of OH concentration. P bananas means what? Negative log of banana concentration. Yes, all right, that's what P means. And so we can use these relationships of log scales, KW, that relationship, and use this magic square that if I know the H plus concentration of a solution is 1 times 10 to the negative 4, then that means its pH is 4. Because I know that because of this relationship right here, the negative log relationship. But what that also means is if the pH is 4, the POH has to be 10. Because pH plus POH equals 14 due to the negative log of KW. KW at 25 degrees Celsius is 1 times 10 to the negative 14. And so then the last bit is, yes, pH plus POH add up to 14, but H plus concentration times OH minus concentration equals, when you multiply those numbers together, it's 1 times 10 to the negative 10. Right? And this is a consequence. So really this equation right here, KW equals H plus times OH minus equals 1 times 10 to the 14, is the same thing as this equation. It's just we take the negative log of both sides. That's it. You take the negative log of both sides. Because I believe a property of logarithms is if you have 2 numbers inside a logarithm multiplied together, can't you separate them and add them? Is that something? Is that a rule? Yeah, so it's the same equation, but you take the negative log of them. So this magic square allows us to relate any H plus, OH, POH, pH. As long as you know one corner of the square, you know everything. Even I will say, I think it's always easier to convert and compare pHs and POHs because you're always just subtracting, versus H plus times OH is a little harder to understand. Okay, so we are going to talk about and hopefully demo some acids and bases and relate it to our everyday life, okay? When we have an acidic solution, H plus concentration is higher than hydroxide concentration. Basic solutions have more hydroxide present, while neutral solutions, they're equal. H plus and OH are equal. So how we calculate pHs depends on what kind of substance is dissolved in water. The whole idea is we need to figure out how much acid is present, how much H plus is present, how much OH is present. That's what we need to figure out. And it depends on what the identity of the substance is. There's two scenarios. So we'll do the first one first, it's easier, okay? To calculate the pH of a strong acid or strong base. You remember those? We talked about those? No? Remember that there are 7 strong acids. Let's just name them real quick. HCl, what else? HBr, HI. Yes, so all of the halogens except HF. Anything else? HNO3, H2SO4, and then our chlorates, HClO3, HClO4. All of these are strong acids. So we're going to make an assumption with every strong acid. They fully ionize. So when you put strong acid in solution, that is the concentration of H plus in solution that allows you to calculate your pH. So it's quite straightforward. So here's an example. All right, HCl fully ionizes. So if I have a 1 molarity HCl solution, what that means is that the H plus concentration in this is also 1 molarity. That's it. We're saying, okay, everything fully ionizes. Same thing with strong bases. Strong bases, basically if there's a hydroxide attached to it, it's most likely a strong base, but it's usually groups 1 and 2 metals. So here are 2 examples of strong bases. Sodium hydroxide is a strong electrolyte. Calcium hydroxide is a strong electrolyte. So it's the same idea. If I have a 1 molarity solution of sodium hydroxide, what is the concentration of hydroxide? 1 molarity. So that is the concentration of hydroxide that I use for my pOH calculation. All of these things fully ionize. Little bit different for calcium hydroxide. If I have a 1 molarity solution of calcium hydroxide, how much hydroxide do I have? 2 molarity, yes, because for every 1 unit of this base you put in, I get 2 bases out. So this is actually 2 molarity of hydroxide. Strong acids and strong bases are easy. We just assume these things fully ionize and they go straight into the pH or pOH calculation. That's it. But you have to identify them as strong. But that's fine because in our weak acids and weak bases coming up, these follow chemical equilibria, big K. So if there is a chemical equilibria going on, I actually have to give you K. So if I give you a K for an acid, that means that that has to be a weak acid. Or if I give you a K for a base, it has to be a weak base. If I don't give you a K, then it's most likely it's a strong acid or strong base because those don't have K values. So yeah, coming up here, we see that for weak acids and weak bases, they have Ks associated with them. So we actually have to do ice tables to calculate their pH. They don't fully ionize. All right, they don't fully dissociate into H plus or hydroxide, so we have to use an ice table to calculate their pH. But it's quite easy. We always approximate. There's no quadratic formula needed. And it's quite predictable on how to do it. Okay, so let's do some sample calculations for pOH and pH. So all of these examples are strong acids or strong bases. So again, we're making an assumption. What is the pH of a HCl solution? HCl is a strong acid. So we're going to make the assumption that whatever the concentration is of HCl is also the concentration of H plus. So we're going to go ahead and say H plus equals 0.0250 molarity. That's what we're going to say. So if we want to calculate the pH, remember pH equals negative log H plus concentration. We just take the negative log of that number. And then we get a number like 1.602. And so remember the rules of pHs. The number of sig figs in your molarity is the number of decimal places in your pH. That the number out front just tells you how big or small the number is. It doesn't actually tell you any sig fig information. All of the significant figures are after the decimal places. Okay, so that is the pH of an HCl solution. Okay, let's also use our intuition a little bit. What did you put into the water? HCl. HCl is an acid. So your intuition says that the water should become acidic. Is the pH we calculated acidic? Yes, it is. Perfect. Okay, let's keep going. Okay, sodium hydroxide. Sodium hydroxide is a strong base. So we're going to make the assumption that all of the sodium hydroxide, when it dissolves, dissociates into that hydroxide concentration. It's a strong base. Basically, you know that we have the same amount of hydroxide and the same concentration of sodium plus as well, because it's a strong electrolyte. So we can go ahead and say that that hydroxide concentration is 0.0175. Okay? But when I negative log this number, am I calculating pH? No, you're calculating what? POH, because this is a hydroxide concentration. So technically, we can't calculate pH directly. We are going to calculate POH, so it's negative log the OH minus concentration we have. So it's negative log 0.0175, which equals negative log 0.0175. 1.73 sig figs, 5.7. Right? So what a lot of students will do is they'll just circle this question, this answer, and they'll just walk on their merry way. But you're better than that. What did you put into water? What kind of thing did you put into water? A base. So your solution should be basic. Is it basic? It isn't. So obviously we went wrong somewhere. No, we're just not done yet. This is your POH. So how do we get our pH? We subtract that number from 14. So pH plus POH equals 14. So whatever that number minus 14 is 12.243. Is that a basic pH now? Yes, it is. So again, use your intuition a little bit to just check that your answer matches. If you put a base into water, it should become basic and nothing else. Right? All right, so all right, let's do the pH of this base, calcium hydroxide. It's also a base. So does this mean that the hydroxide concentration is 0.003? No, it's not. It's actually 0.006 because there are two hydroxides there. Two hydroxides. So that's the only difference in this question, that this base actually has two hydroxides per every unit. So be careful there. Sodium hydroxide only has one, so you're fine. And so yeah, POH that. So negative log 0.006, so 2.222. Don't stop there. That's an acidic pH. We just calculated POH, so we have to subtract from 14 to get that the pH is actually 11.778 instead. So yes, it is basic. Oh, only 2 sig figs. Yes, it's only 2 sig figs. So 0.78 because it's 0.0030. So just 2 sig figs. All right, so acids, bases, okay. Can we have a negative pH? So concentrated HCl has a molarity of 12.1 molarity. What is the pH? So HCl, this is its HCl concentration. So just like before, we can calculate what is the concentration of H plus here. HCl is a strong acid, so it's 12.1. So if we wanted to calculate the pH, we simply do log 12.1, and if you do that, I think you do in fact get a negative number, and that is quite okay. That is quite okay. You get negative 1.0, how many sig figs? 3.83. And that negative pH is quite okay. It just means that you have a really, really, really concentrated acid solution here. It's not super common to report negative pHs, because typically if we're working with really concentrated acids, we'll just straight up tell you the concentration. We'll say, you know, like 10 molar or something. We'll just say that. We're not going to tell you the pH. But when we're working with really dilute solutions, sometimes saying the pH instead of the concentration is easier because concentrations can be really small. Okay, So I was going to do the demo right here, but I actually want to do 2 more questions, and then I'll do the demo. Yeah, 2 more questions, then do the 2 or 3, and then do the demo. Okay, so let's relate pH to KSP as well. So remember, KSP, SP stands for what, do you remember? Solubility product, so it's how much solid dissolves in water. So if I tell you that the KSP for a saturated solution of calcium hydroxide is this number, it's not super soluble, so KSP equals 5.5 times 10 to the negative 6. If we have a saturated solution of calcium hydroxide, we have a big hunk of solid in the middle, but then we have a bunch of ions dissolved on the outside. If I want to figure out what the pH is, it makes sense. If I figure out how much hydroxide is dissolved in here, I can figure out the pH. So really, this question is a molar solubility question. Let's figure out what X is in this ice table, right, when we ice table it. Remember how we ice tabled with molar solubility and dissolving solids. We dissolve an N amount, a random amount of solid into our water. A little bit of it dissolves, so that means the reaction has to go which direction, forward or backwards? Has to go forward, so my X's are going to be minus X, plus X, but then it's going to be plus 2X. So at equilibrium, we have an N minus X of solid, an X amount of calcium, and a 2X amount of the hydroxide. So when we write out our KSP expression, KSP equals calcium 2 plus concentration and hydroxide concentration, but it's squared. Now I want to put those X's in each of those concentrations like we do NEK and ice table expression. Remember, we can just ignore this N minus X because solids do not go into the ice table or into our KSP expression. So we get that this KSP expression is X times 2X squared equals 5.5 times 10 to the negative 6. We can easily solve for X. This is equal to 4X cubed. And so if you solve for X, you get that X is equal to, I think, 0.011 molarity. But is this molarity so this would be the molar solubility. If I just asked you what is the molar solubility of calcium hydroxide, that's what you would say, 0.011 molarity. But is that the concentration of hydroxide? It is not. What is the concentration of hydroxide? It's actually 2X. That's what I want. The concentration of hydroxide is 2X, so it's equal to 0.022 molarity of hydroxide. So if I negative log this number, I can get the POH. So POH equals 1.66. So therefore, if you subtract from 14, you get a pH of 12.34. All right? So that makes sense. Calcium hydroxide is a base. You put a base in water, and the solution should become basic. Yes. All right, so we will do, I don't want to do those two. Can I make it? Can I make it? No. Okay, we'll just do the demo then. Yeah, we'll just do the demo. Yay. Okay, so demo. So here's the thing. You put an acid in water, the solution should become acidic. You put a base in water, and it should become basic. So let's do the demo, and you can be wondering why I have a monster up here. All right. Okay, so I have a reaction up here. CO2 is a really peculiar compound. All right, CO2. CO2, when CO2 reacts with water, it becomes this compound, H2CO3. Does anyone know the name of that? So CO3 2 minus is carbonate. So when there's 2 hydrogens, H plus is attached to it, it becomes an acid. So that is actually called carbonic acid. So CO2 is slightly acidic because when CO2 reacts with water, it becomes carbonic acid, all right? So anything with dissolved CO2 and it has a little bit of carbonic acid. So I want to show this demo, but in order to do it properly, I got to show you the range of pHs and colors. So I have a bunch of solutions up here. So all of these solutions just have water in them right now. It's just pure plain tap water. So what is the pH right now at 25 degrees Celsius? 7, pH neutral, all right? So this is the color it looks when it is pH 7 neutral. So I'm gonna add a drop of sodium hydroxide. Sodium hydroxide's a what? Base, so it should turn the water basic. So I just want you to see what that looks like. Base, ooh, yes, ooh. All right, drop of HCl, hydrochloric acid. It should turn the water acidic. So I want to show you what acidic looks like. Okay, got to use the same one. Acidic, okay? All right. Oh, we like that. We like pretty colors. Okay, so I told you the little background story about CO2. As humans, what are our exhaust products? What do we inhale? Oxygen, but what do we exhale? Carbon dioxide, yes. So we exhale a little bit of carbon dioxide. Okay, and what did I tell you about carbon dioxide? It's a little bit acidic. So what do we think is going to happen when I blow into with this scientific device? When I blow into this water, what should it do? It should get acidic. Okay, they didn't give me a cover. Did it turn? There we go. Yeah, see, it turned. Okay, what else has CO2 in it? So that was my breath, okay, acidic. What else has CO2 in it? So what is as good as on a really hot day after you've been like working out on the farm and just like a nice cold bubbly soda? There's nothing better than that, right? But here's the thing, sometimes when the soda is too cold, it like burns my tongue. When it's too cold, it's like spicy. Did you ever get that? Yeah, you know what I'm talking about? Where the CO2, it's so cold, those CO2 bubbles like burn my tongue, all right? And so a lot of sodas are so tasty because of how acidic it is. And it's because if I read the first ingredient on this LaCroix, really there's like no ingredients in a LaCroix. But the first ingredient says only carbonated water. So there's only CO2 and water in essence inside here. So what do we think will happen when I add a drop of this to the thing? It should turn acidic, yes, because there's a lot of dissolved CO2 in it, right? Because it's a soda, carbonated. Okay, so I'm going to add a little bit of LaCroix. What happened? Oh, fudge. Okay, they will clean that up. Okay, let's, we will do this one. Where's my other one? Where's all my stuff? This one turned not basic anymore. Where's all my stuff? Yeah, okay, we'll just use this one real quick. Okay, we'll do that again. Sorry. LaCroix. Acid. Yes, acidic. Would you say that's acidic? That is very acidic. All right, okay. So what else do I have up here? I have a specialty Monster energy drink. Have you ever heard of this? It's the nitro kind. The nitro kind. So instead of carbonation, CO2, they use N2 bubbles, all right? So instead of carbonation, it's nitrogen. So nitrogen, not an acid. Where did my pen go? There it is, okay? So in this nitrogen monster, the bubbles are actually made of nitrogen gas. So other examples of nitrogen-containing drinks is like a Guinness. If you ever had a Guinness, the bubbles are smaller and typically smoother, all right, because it's made of nitrogen. Apparently there is a nitrogen Pepsi too. It's just not as, it doesn't burn as much, and it's because nitrogen isn't an acid. So what do we think that this nitrogen monster is going to do when I do the test? What do we think? I don't know. We'll see. We'll see. I don't know. I did this for the first time a couple weeks ago. I didn't know it would happen. The first time I did this, someone in the balcony said, I know that sounds like a nitro monster up in the balcony. They know the difference. Okay, so we'll see what this nitrogen monster does. Do I have one more? All right. What do you think is going to happen? Nothing? Okay, we'll see. Aww. Aw, so why did it turn acidic? Dr. N, you said that there was nitrogen in there. Well, it is. Okay, so the first ingredient is nitrogenated water, sugar, glucose, and then the fourth ingredient is citric acid. Okay, so so this Nitro Monster energy drink is also acidic, or else we wouldn't enjoy drinking it as well. So we'll stop right there. So if anyone would like this Monster or LaCroix, you can go ahead and take them. Someone better take this Monster. I don't want it. Okay.
Thank you very much.